Hello everyone. Welcome to this lecture on digital electronics. In today's lecture, we are going to discuss about full adders. So already in the previous section, we have discussed about half adder. So initially, we need to know what is an adder and where it is being used. Mainly, when we consider a computer system or a calculator, we have the processor, and this processor has the ALU unit, arithmetic and logical unit, in order to perform the arithmetic and logical functions. So, the basic arithmetic operations are adders and subtractors. So, that is the place where we require adders basically. Two types of adders are there, half adders and full adder. So in the previous section, we have discussed about half adder, and in today's section, we'll be discussing about full adder. So full adder is a combinational circuit that can add two binary digits and a carry bit. So altogether three bits and produces a sum bit and a carry bit as the output. So here we'll be adding, in a full adder, we'll be adding three bits and we'll be getting two outputs. So three input terminals will be there and two output terminals will be there. Then for realizing a full adder, we need XOR gates, AND gates as well as OR gate. Again, this is the procedure to design a full adder. So first, we'll be writing all the conditions as truth table. Then we'll be drawing a K-map. Form the Boolean expression for the K-map. Then draw the circuit diagram. This is a procedure which is being carried out to design any digital system. So first, we have to write all the conditions. That is a truth table. As we discussed earlier, here the number of inputs is 3. So 3 variables we are using. That is 2 will be input and 1 will be the carry of the previous addition. So altogether 3 inputs. And if 3 inputs are there, 2 power 3 combinations of input possibilities will be there. So 2 power 3, it varies from 0, that is 8, varies from 0 to 7. And we have written the binary corresponding value for the decimal values. This is for 0, this is for 1, 2, 3, 4, 5, 6 and 7. And as like the half adder, here we will be doing the same addition. That is logical OR operation will be carried out. Logical OR operation states that when both the inputs are 0, the sum will be 0 and carry will be 0. If any one of the input is 1, the sum will be 1 and carry will be 0. So all these cases deal with the same thing, that is single ones, right? And here we have two ones, addition of two ones. When we add two 1, then sum will be 0 and carry will be 1. Here also the same case, to 1 plus 1 plus 0. So two ones we will be adding that is the 2 which is 1 0. 0 will be writing it in the sum and carry will be writing and 1 will be writing as carry. Similarly, when all the values of the input is 1, the sum will be 1 and carry will be 1. Can say even like 3 and the binary value corresponding to that for this case. Now we have to draw the K-map. So K-map will be drawing it for the outputs. Here how many outputs do we have? We have two outputs, sum and carry. Right? So this is the K-map for sum and this is the K-map for carry. So similarly, the same manner here, since it is only one variable, it can take either 0 or 1. Either 0 or 1. Here we have two variables and four combinations we can have 0, 0, 0, 1, 1, 1 and 1, 0. Here we'll be writing 1, 1 and then 1, 0 because we need to have single bit variation between two states. If we write after 0, 1, if we write 1, 0, both the bits are varying. Both the bits are changing, which is not acceptable in K-map. That is why we have written 0, 0, 0, 1, 1, 1 and then 1, 0. Now, as like the previous case, we will be writing if it is 0, 0, 0, this is the cell corresponding to that. 0, 0, 0, sum is 0. So, we have left it out. Wherever we have ones, we have marked it. And after that, we need to group, right? After grouping, write it in a standard form. Similarly here we have three groups, and for this group the common term in the row is A and the common term in the column is C in. So we have A C in as a min term. And for this group we have B C in as the common term. Only the column is common, row is not common. So B C in is another min term. Then if we consider these two uh, columns, that is if we consider this group, A is the common term and B is a common term here in this column. So AB is another min term. This is how we have to write the Boolean expressions from the K-map. So this is the Boolean expression corresponding to the K-map, and this is the expanded form, and from this, after applying laws, taking common terms and simplifying, we'll be getting this one. So we have realized, so here two XOR gates are there, right? So two input, two XOR gates are being used here. And here AND gates, here one AND gate, two and three AND gates all together, right? And then all the min terms are being given to an OR gate. This is the design procedure of full adder. And as like half adder, it also has different applications which provides the facility to add carry from the previous stage, which is not available with half adders. Then power consumed is relatively less. Full adder can be easily converted into half subtractor just by adding a NOT gate. It is one of the important parts of multiplexer. Full adder performs operation at higher speeds. And this is for your assessment. Take the assessment and practice it. Thank you.